this one, let's look at this example on how we can create a tree and make that tree become a two-way table. And then from the two-way table, we can use it to answer the conditionals that we looked at a second ago. So in this particular problem, it says two office assistants are responsible for getting the daily target list to the appropriate principals by 3 p.m. Harrison works on the list 30% of the days, and Laura works on the target list the remaining percent of the days. Harrison fails to get the list to the correct principals in time 10% of the time, which ironically would make him tardy with the target list. Laura, not much better, manages to get the target list to the correct principles 92% of the time. So if I want to fill out this table right here, it's going to be really hard to go through this problem and do that because the percentages that you're looking at aren't all going to be these joint ones, and that's what we're trying to fill out. So an easier way to do this is to make a probability tree. And here's what we have to do. We need to realize that these are what we call disjoint events. And disjoint just means that if one occurs, so if you're tardy with the list, you can't be not tardy with the list. Likewise, these two people are disjoint events, where Harrison is not going to be Laura, and Laura won't be Harrison. So the disjoint events are represented on the outside of the table. Now, what we're going to do is we're going to go back through here and look at the information that was given. They tell us that Harrison works on the list 30% of the time. And that means that if he works on the list 30% of the time, then out here, that should be 0.3 for my total. That is a margin. I know it's going to be 30%. If he works on it 30% of the time, Laura works on it the rest, that puts her at 0.7. So this is just the easy part to get out there. What makes it hard is that Harrison fails to get the list of the correct principles in time 10% of the time. So he's tardy with the list, which would be here. You would think 10% of the time, but you have to remember that you're counting for this 30%. So the easiest way to show this is to actually make a tree. Here's what we're going to do. The first thing we're going to do is we're going to give these variables in terms of our complements. So I'm going to let this variable, tardy with the list, be t. Not tardy with the list, t complement. Remember, not tardy. I'm going to let Harrison be h. And if it's not Harrison, it's Laura, but I'm going to use the complement notation, so I'm going to call this HC. We know that means Laura. So here's how we start this. In our tree, Harrison is here, Laura, HC is here. And when we do this, we know that Harrison handles the target list 30% of the time, and Laura handles it 70% of the time. So that's the first branch. From there, the list is either going to be tardy from Harrison or not tardy from Harrison. It's tardy from Harrison 10% of the time, so that's T. Not tardy means it's on time. So 10% of the time is tardy. And if it's tardy 10% of the time, that means it's not tardy 90% of the time. And then from Laura, who is not Harrison again, it can either be tardy or not tardy. Well, it'll be tardy from Laura. She turns it in on time 92%. So not tardy is 0.92, and tardy is 0.08. And remember, I'm getting these because these have to add up to 100%. Just like these have to add up to 100%, and these branches add up to 100%. And now, so here's the thing I'm going to do. I'm going to assume independence. And that literally means that I can multiply every one of these branches. So in this first branch, I'm going to multiply 0.3 times 0.1. In this branch, I'm going to multiply 0.3 times 0.9. And when I do that, lock these together. And when I do this, here's what I get. 0.3 times 0.1 is 0.03. 0.3 times 0.9, 0.27. Notice that if you were to add these two up, they equal the 30% that sit at the top of the branch. And so if I come back over here real quick, I want you to notice that this right here, we read the branch, this is Harrison and tardy. So that's H and T, which if you look right here, H and T now, we can know that's going to be 0.03. Likewise, this is Harrison and not tardy. That's 0.27, and look what they add up to. They add up to that 30%. So we're going to do the same thing on these two branches here. We're going to multiply the branches across. I'm going to multiply them across. I get 0.7 times 0.08 and 0.7 times 0.92. I'm going to multiply 0.7 times 0.08 I get 0.056. I'm going to multiply 0.7 times 0.92. I get 0.644. And again, if you add those branches up, you're going to get your 0.7 across. So here, not Harrison, which is Laura, and Tardy, 0.056. Not Harrison, again, Laura, and not Tardy, it's 0.644. And now what I can do is I can find how often they're going to be tardy with the list. So we see that they're tardy with the list here, 0.086. And here they're not tardy with the list, 0.914. If you add those up, you get 1.00. So this is creating the actual table, and now we can answer these questions. And the first question says this: given that the list is late, what is the probability that Harrison worked on the list? So remember, given, probability of B given A. In this case, I want the probability that it's Harrison, that it's late. Probability of it's late would be T. What is the probability that Harrison, which he would be H? So what is this telling us to do? Restricted to a late list. I'm only interested in late lists. Well, the late list column is tardy right here, that T column. That's 0.086. And then I want to be interested in Harrison making it late. And that's 0.03. So for Harrison to make it late, it's 0.03 divided by 0.086. Harrison is late with that list. If it's late, there's almost a 35% chance that it was Harrison that made it be late. And then if you look at the next one, is a late list independent of the assistant? Justify your answer. So I just want to know, does it matter who does it, or is one person more late than the other? Well, I'm just checking independence. That's all it is. Check independence here. Remember, I'm going to use the condition, which is probability of H given T already given to me. That's given to me. And I'm going to show that it equals the front value, the probability of H. In this case, the probability that Harrison was with the list. So probability of H given T, 0.349. And we can see the probability of Harrison is this right here, which is just 0.3. They're not equal to each other. So because they're not equal, we would say no, they are dependent.